Hello and welcome to the Unit 9 podcast on section 19.3. Today we're going to talk about the pH scale. I'm Mr. Sakaguchi,
I'm Mr. Lin.
and here we go. Okay, so before we do pH, let's talk a little bit about water itself. Water, as it self-ionizes, we talked about how, in neutral solutions, the hydrogen and hydroxide ion concentrations are equal, and this is because of our equilibrium reaction with water in itself. Because this is an equilibrium reaction, we can write an expression for it, and this is known as Kw because it's specific for water.
And as a result, you get 1 times 10 to the negative 14 for your Kw, which is from the KEQ. And then when you find out what the concentrations are for your hydrogen and your hydroxide ions, it winds up being 1 times 10 to the negative 7. And that's where you guys will explain a little bit later about where the pH for 7 in neutral water comes from. Notice that for acidic and basic solutions, whenever you multiply the two together, they always wind up equaling Kw.
And Le Chatelier's principle will apply where, we can do the teeter-totter thing.
Right.
There's pH scale and there's also pOH. pOH is not used as well. pH is the one that's used. pH is equal to the negative log of the hydrogen ion concentration. pOH is basically the same thing, but instead of hydrogen ion concentration, it's the molarity of hydroxide ion.
For acidic solutions, the pH is going to be less than 7, okay, and as a result, the pOH is going to be greater than 7. Don't confuse the two. I noticed that a lot of students early on, before they've gone into this section, think that a higher pH value means more acidic. That is not the case. Lower pH means more acidic. Basic solutions, the exact opposite is true, where the pH is greater than 7 is basic, and as a result, the pOH is less than 7.
We can also take the antilog and solve for hydrogen ion concentrations. So if I know the pH, if I take the antilog of the negative pH, that will give me the molarity of the hydrogen ions. And the same thing, if I take the negative antilog of the negative pOH, that will give me the hydroxide ion concentration. pH plus pOH always equals 14.
And that's related to when we talked about the Kw and the hydrogen and the hydroxide concentrations multiplying together always winds up being Kw of 1 times 10 to the negative 14. Same thing here, pH plus pOH equals 14.
There are different kinds of calculation types. If I want to calculate the pH from the hydrogen ion concentration, I just have to take the negative log. If I want to calculate pH from the hydroxide ion concentration, I can calculate the pOH first and then subtract that answer from 14.
Calculating for the pOH from the OH concentration, just like you do with the pH, it's just the negative log of the OH concentration. And then calculating for the pOH from the H plus concentration, you can do, again, negative log of the hydrogen concentration, find the pH, and then subtract from 14.
There are other more complicated ones as well. If I want to calculate the pH from a strong acid, I look at the dissociation and I look at the mole ratio to get the hydrogen ion concentration. And then once I have that, I can just take the negative log of that. If we're doing it from strong bases, I can do the same thing. I can look at the reaction, figure out the hydroxide ion concentration from the original concentration or moles of the base undissociated. And that'll give me I can calculate pOH, and then I can subtract that from 14 to get the pH.
Realize that when we're talking about the mole ratio, we're talking about the subscript that would be associated with either the hydrogen ion if we're dealing with an acid, or the hydroxide ion if we're dealing with a strong base. And whatever subscripts are associated with it, we would multiply that by our molar concentration of our acid. When you want to calculate for the pOH from a strong acid, you could just find the pH of our strong acid first, and then subtract from 14. And then to calculate for the pOH from a strong base, all you got to do is negative log of that OH concentration. Again, dealing with those mole ratios, multiplying by the subscript associated with the hydrogen or hydroxide ion.
We can also use pHs to calculate Ka. Let's say we had this acid at this molarity, and here's the pH. What is the Ka? This would be our reaction. Okay. Then we can write our equilibrium expression, And we know that the H plus concentration is equal to the negative, the antilog of the negative pH. So we know our initial hydrogen ion concentration. So what we do is we make what we call an ice box. ICE stands for initial, change, and equilibrium. So what we do is we write out our reaction. We have our initial conditions, so we have 0.1 molar, 0 and 0. The H plus concentration represents what happens at equilibrium. And because there's a 1-to-1 molar ratio between H plus and HCOO minus, these are going to be the same. And if we got this, that means that we had to subtract this from the initial. Then what we do is we add up as we go down the box. So we add I and C to get the equilibrium situation. So we subtract the 4.2 times 10 to the negative third, and we add those to here. And then we have our numbers to plug in into our Ka expression to solve for Ka.
Now, do realize that pay attention to the ice part where it states initial. That's why we have 0 concentration for the hydrogen ion concentration, and for the conjugate base, they're at 0 because nothing started yet. That's the initial. Then you take into account the changes and then solve and plug in the numbers to get your Ka value.
And we'll do some of these in class.
Right.
Measuring pH, we can measure them in many different ways.
Right, being pH paper, litmus paper, etc. Litmus paper or pH paper is easily found at the market because it's used in cooking. And basically what you do is, a lot of people think you just dip it into the solution. Proper lab practice is you use a pipette and pull it out of the solution and drop it on the litmus paper. That way you don't mix solutions and taint your sample.
And we can also use pH meters as well.
Which are a lot easier.
And if you have a pool or a jacuzzi at home, you probably have pH measuring equipment.
Right.
And that's it.